By the end of this lesson, you should be able to resolve a force into the effective component forces, describe situation where forces are in equilibrium, determine the resultant force, solve problems involving situations where the forces are in equilibrium. Why does the book stay on the inclined plane and not slide down? Why is the lady dragging her traveling luggage instead of pushing it? A book is at rest on an inclined plane. What are the forces acting on it? The weight W of the book acting vertically downwards and the normal reaction R acting on it by the inclined plane. There is also frictional force F prime acting along the plane. Why doesn't the book slide down? The forces acting on the book are balanced. This can be shown by resolving the weight of the object into two components, one along the inclined plane and the other perpendicular to the plane. In this case, the component F1 is balanced by the frictional force F prime, and the component F2 is balanced by the normal reaction R. The resultant force is zero, and thus the forces are in equilibrium. W is resolved into two component forces, F1 and F2, which are perpendicular to each other. Since sine theta equals F1 over W, F1 equals W times sine theta. Since cosine theta equals F2 over W, F2 equals W times cosine theta. If the weight of the book is 12 newtons and the angle between the inclined plane and the horizontal is 30 degrees, calculate its frictional force. Frictional force is equal to W sine theta. The frictional force is 60 newtons. Why is she dragging her bag instead of pushing it? Are the forces acting in equilibrium? The applied force F can be resolved into two components, that is, F1 at right angle to W and F2 at right angle to F1. In this case, the forces are not in equilibrium. Horizontally, if F1 equals F prime, the resultant force F1 minus F prime is zero. The luggage moves with uniform velocity. If F1 is greater than F prime, the resultant force F1 minus F prime is not zero. The luggage moves with increasing velocity or it accelerates. Vertically, W equals to R. The resultant force in the vertical direction is F2. Since F2 acts upwards, as a result, the luggage appears to be lighter and easier to move when it is dragged. When the luggage is pushed, the applied force F is acting in the opposite direction. Horizontally, if F1 equals to F prime, the resultant force F1 minus F prime is zero. The luggage moves with uniform velocity. If F1 is greater than F prime, the resultant force F1 minus F prime is not zero. The luggage moves with increasing velocity, or it accelerates. Vertically, W equals to R. The resultant force in the vertical direction is F2. Since F2 acts downwards, as a result, the luggage appears to be heavier and more difficult to move when it is pushed. The picture frame hanging on the wall is in a state of equilibrium, and thus all the forces acting upon the picture frame will be balanced. If the tension in both strings is 10 Newton and the angle the string makes with the horizontal is 30 degrees, what is the weight of the picture frame? Since the picture frame is in equilibrium, T1 times cosine 30 degrees equals to T2 times cosine 30 degrees, and W is equals T1 times sine 30 degrees plus T2 sine 30 degrees. Therefore, W equals to 10 newtons. If the same picture is hung in a different way and the angle between the strings and the picture is 30 degrees, what is the tension in both strings? Assume the strings are identical. Since the picture frame is in a state of equilibrium, T1 times cosine 30 degrees equals T2 times cosine 30 degrees, and W equals to T1 sine 30 degrees plus T2 sine 30 degrees. Therefore, W equals to 10 newtons.